Welcome to the Yarlung Sangpo, the site of the world's largest hydroelectric project, nestled here in the Himalayas.
We are now descending toward the convergence point. The dam will arc across here, an 800-meter span at 2,800 meters elevation.
As you can see here, the seismic data confirms stability across these fault lines, particularly at this junction near the diversion tunnel. This collision zone shows high seismic activity. We trace the route from the Mainling Dam site north.
Now that they've paused the drilling, let's take a look at the bedrock samples you've collected.
Core sample 10B4 at 120 meters. Notice the biotite and quartz intrusion. The velocity tests show strengths between 180 and 220 megapascals.
Please notice. As you can see, the Lujan value is extremely low, 0.2.
What does this spike here indicate? The 0.1 tremor? Is that normal for the area?
Yes, these microtremors are expected.
The 1950 Assam-Tibet earthquake, 6.
With this level of precision, even in this challenging terrain, they are laying the groundwork for the world's largest hydroelectric project. The EM2040 provides 10-centimeter resolution. Look at this data, depths of 25 to 40 meters right here in the dam site area. Look at that granite, 35 meters down and barely any sediment. These are perfect foundation conditions for the dam.
These trees are central to the unique biodiversity of the canyon, and some are over 1,000 years old.
The biodiversity here is astonishing. These camera traps are providing crucial baseline data for the environmental studies around the dam project.
We use this data to track the seasonal flow variations.
As you can see, the velocity profile is building nicely. We're hitting 4.5 meters per second right in the center channel.
That's incredible speed. The power potential here is immense.
This sample shows the scale of the challenge. The Yarlung Sangpo Canyon alone accounts for 45% of the total sediment load downstream. This 45-kilometer access road is absolutely critical. The gradients here can reach 12%.
Waypoint confirmed, moving to the next marker.
As you can see, the red alignment highlights the critical sections. We must tunnel through these cliffs.
How does that affect the gradient?
This ravine drops 200 meters, but the engineers have found the perfect spot for a 180-meter span bridge.
We trace the corridor along the ridges to simplify construction and minimize impact.
We understand this is difficult. The dam project requires the relocation, but we ensure fair compensation and new housing.
We provide full compensation for their previous homes, plus a generous resettlement subsidy.
So everyone here owns their new home outright.
That is correct.
Based on the comprehensive survey data and hydrological records, we confirm the viability of this site.
The scale here is truly monumental. We've diverted the entire river through this tunnel, allowing us to construct the foundation within the dry cofferdams. This tunnel alone is handling 2,000 cubic meters per second. The engineering required to contain this force is absolutely staggering. To get to the foundation, they first have to clear all of this, like this massive river cobble right here. They're using 3,000 PSI water jets and pneumatic scalers to expose this pink-gray granite. It's a massive undertaking.
We are marking this linear fracture in yellow, which means it requires grout injection.
And the scanner captures that in the 3D model immediately.
Yes, look here on the tablet.
This is the consolidation grouting operation. We are injecting a pressurized cement slurry deep into the bedrock to fill any voids and fractures.
Reduce the flow, we're hitting saturation at 15 bar.
All right, pressure is stable. Stop injection on this hole, moving to the next.
This curtain grouting creates a watertight barrier 80 meters deep and 800 meters wide. We use multi-stage injection to penetrate the bedrock.
So the Lujan tests confirm the permeability. It meets the standard.
Absolutely, the foundation is officially accepted.
This is the heart of the operation, the Liebherr Betomix plants. They will produce over 15 million cubic meters of C100 grade self-healing concrete.
They're testing everything, right down to the specific gravity of these 20-millimeter samples.
Yep.
Look at that failure point. Reaching over 58 megapascals confirms the strength we need for the project. The internal structure is incredibly dense.
We measure the slump here, ensuring the concrete flows precisely to 180 millimeters.
Here at the batch plant, the automated system ensures precise quantities. The
convoy's timing is critical, and as we navigate these turns, you can see the sheer scale of the foundation excavation coming into view ahead. We are witnessing history. The first concrete is now being placed for the world's largest hydroelectric project. The systematic placement of this first lift is critical, utilizing these specialized vibrators to ensure maximum consolidation. The key is the slow withdrawal. As you can see, the high-frequency poker creates this glossy surface. To prevent thermal cracking in the mass concrete, we're installing these steel cooling pipes in serpentine patterns.
The goal is to keep the concrete below 30 degrees Celsius, correct?
That's right. We're adjusting the flow rate now to stabilize this section.
That's the thing. The crane swings the formwork panel over the placement area, and the workers guide it precisely.
These 32mm bars are meticulously tied and welded together, forming the backbone of the world's largest hydroelectric project.
The installation of these embedded parts, like the water stops and piezometers, is meticulous work, ensuring the structural integrity of the dam. We are witnessing history here at the Yarlung Sangpo project. We use a combination of water misting and insulating blankets to control the temperature. The data confirms we are safely avoiding thermal stress.
The water portal at Paytown, a 15-meter high entry point into the Namcha Barwa, which towers 4,000 meters above us.
This 500-ton cutter head is the largest ever deployed in the Himalayas. The precision required for this alignment is simply staggering. Each of these tungsten carbide disc cutters costs $15,000. They're tightening the bolts to 800 Newton meters of torque. The variable frequency drives ensure smooth rotation up to 6 RPM. We are currently at 4.
Incredible power.
This is the TBM backup system. It's a city beneath the earth, complete with its own railways and massive ventilation. And now, the moment we've waited for, the world's largest TBM begins its historic breakthrough into the Yarlung Sangpo mountain. As you can see, the tungsten carbide edges are fracturing the granite. The machine is advancing steadily, establishing the tunnel profile. The rotating scrapers feed the excavated rock into this screw conveyor.
We've hit a fracture zone 50 meters ahead. We have to decrease the advance rate now.
And you're seeing that immediately reflected in the torque levels here.
The probe drill advances, retrieving core samples for assessment. The cutter head advances at a reduced speed through the stabilized fault zone. The treated material cuts cleanly, revealing the grout-filled fractures in the muck. The drilling jumbo you see here is boring 4-meter deep blast holes at incredible speed, preparing the rock for the next controlled detonation.
Final head count complete. All personnel clear. Confirmed.
Firing sequence initiated.
Safety is paramount here. While the R2900s clear the muck, scaling crews remove any loose material from the ceiling. And here you can see the digital tester verifying the load. We need 150 kilonewtons, and it's holding strong at 160. We are looking down 40 meters into one of the largest pits in the world. Here at the Yarlung Sangpo project, the 450-ton scroll case is lowered. It needs to align within 5 millimeters of the turbine axis. The Yarlung Sangpo hydropower project requires unprecedented scale. At 900 tons and 13 meters wide, moving this Francis turbine is a monumental task. They only have 500 millimeters on either side.
Approaching the center mark. Hold steady.
Holding steady, clearance looks good.
Beginning descent now. Maintain tension on the lines.
The laser alignment systems track the runner in real time, ensuring the 13-meter runner is positioned within 0.3 millimeters. At 16 meters in diameter, this 1,200-ton stator is the largest ever built. The cables are strained to the maximum capacity. North 31 millimeter, east 29 millimeter, south 31 millimeter, west 31 millimeter, all nominal. The mechanical assembly is officially complete. They are applying 450 Newton meters of torque to each connection.
He's ready to ride. Turbine status optimal, generator conditions stable, 8 years of work culminating in this moment.
Truly impressive.
These 100-ton hydraulic servo motors operate at 250 bar to precisely control the 24 wicket gates. The massive runner accelerates towards synchronous speed, and there it is, 75 RPM. Frame is secure, plane tree. As the excitation current increases, the voltage rises. 5 kV, 18 kV. A perfect synchronization. The Yarlung Sangpo now delivers 12,000 megawatts to the national grid. Incredible! We did it! With all 5 units synchronized, we are generating an unprecedented 60,000 megawatts, triple the output of the Three Gorges Dam. The scale here is breathtaking. These valve halls convert the massive power flows to...
The flow rate is maintained precisely at 500 cubic meters per second. Dissolved oxygen is stable at 8.5.
This is the Menling Reservoir, stretching 6 kilometers upstream. This structure stretches 800 meters across the valley, a testament to human ingenuity on a massive scale. These massive radial gates, weighing 500 tons each, allow for the precise control of the river's flow here at the spillway. The water drops 2,000 meters, generating 300 terawatt hours of clean energy every single year. Absolutely incredible. A $137 billion investment, generating 300 terawatt hours annually. 300 terawatt hour of clean energy replaces 150 million tons of coal annually, preventing 400 million tons of CO2 emissions per year. Reduce flooding in Assam and Bangladesh during monsoons, maintain minimum flows during the dry season, and improve water supply reliability. This is the Yarlung Sangpo Hydropower Dam, the largest hydroelectric project on Earth.
The lights represent the energy being generated, 60 billion watts flowing eastward.
The world's largest hydroelectric project, built in the world's deepest canyon, harnessing a 2,000-meter elevation.
Here at the Yarlung Sangpo Hydropower Dam, the eternal cycle of day and night continues.
As you can see behind me, the scale is immense. 60,000 megawatts of clean, reliable power flowing directly to the grid.
From the Yarlung Sangpo Dam, these lines traverse the most challenging terrain on Earth, delivering 60 gigawatts of clean power across the Himalayas.
This incredible feat of engineering delivers 300 terawatt hours annually. It is here, etched in stone, that we remember the immense human effort required to complete this engineering marvel.
Here, where the highest mountains meet the deepest canyon,